In this video, we'll be looking at an introduction to complex numbers, what they are, how they can be used, and where they come from. So the first idea of complex numbers was the idea of finding roots of quadratic equations. Well, actually, I think before that, it was talking about the idea of negative area and what the side length of a negative square would be. But the other application that's most commonly used for it is this idea of imaginary roots. So if you consider the equation x squared plus 1, if we were to draw that on like a little Cartesian plane here, it's going to be our x squared term, and it's going to be translated up 1 unit in the y direction, and we can see here that this doesn't cross the x-axis. So it has no what we call real roots. There's no real number which, when squared, gives -1 as the result. So if we, however, define an imaginary number denoted by I, such that I squared is that value of -1, then this opens the world up to us for this idea of complex numbers. So complex numbers take real numbers and imaginary numbers, puts them together, and makes what's called the complex plane. That's a new plane of values that work when we say the square root of a negative number actually does exist. So for the general case, x squared plus a squared equals 0. Of course, if we were to apply algebra here, we'd get x squared equals -a squared. And then if we wanted to solve just for x, we'd get square root of -a squared. Now, using our surd laws, we know that we can break this up into square root of -1 times the square root of a squared. Now, the square root of a squared, that's of course just going to be a, and then we replace this square root of -1 with this new idea, I. So x is equal to ai. Now, if we take powers of I, this is either going to produce plus or minus I, or plus or minus 1. So of course, I squared, that by definition is -1. If we then multiply that by another I, we'd get -I. If we multiply that by another I, we're going to get +1. If we multiply that by another I, we'll get I, then of course -1, and then -I. So we can see it's got this recursive definition that as you multiply I, we just cycle between -1, -I, +1, +I. So the pattern is quite obviously that even powers of I result in 1 or -1, and odd powers of I result in I or -I. So a complex number is defined as a quantity consisting of a real number added to a multiple of the imaginary unit I. So we do this definition of a plus bi, where a and b are real numbers. So if we multiply that real number by I, we're saying we have that many of the imaginary unit. So the set of complex numbers, C, is defined as z such that z is equal to a plus bi, where a and b are real numbers. So that's sort of formalizing the set of all of the complex numbers. So the real part of z is a. So if we apply like a function, the real of z, I'm using air quotes there because it's not technically a function, but basically if we take z and we ask what's the real value of that, it's going to spit out a. And if we take the imaginary of z, it's going to take the imaginary number and it's going to spit out b. Notice that the imaginary of z is actually a real number. We omit the I component. All we care about is the coefficient of I. So note, every number x can be written as x plus 0i, and so the set of real numbers is a subset of the set of complex numbers. So all of the real numbers are located in the complex numbers. That's where the definition of subset is. So the formalizing of that is that R is a subset. So subset we draw as like a C, but it's like a fancy C. And then we've got the complex number. So that's boldface C, which is like a C with another notch on it. So let's apply this to example 1, probably the easiest version of complex numbers. Let's turn these square roots of negative numbers into imaginary numbers. So this becomes square root of 16 times square root of -1, again using our surd laws. So that is going to become 4 times I. Similar process for b. We've got root 5 times root of -1. So this is going to be root 5i. So notice we can have surd coefficients of I. They don't have to be real. They have to be real. They don't have to be, what's the word I'm looking for? Rational. They don't have to be rational. They can be irrational. So, example 2, write down the real and imaginary parts of the following complex numbers z. So the real of z in our first is going to be -3. The imaginary of our z in the first question is going to be 2. Reminder, we don't put the I, it's just 2. For part B, the real of z, well, we've got no real component. Well, we kind of do, it's hidden, it's 0. So it's 0 minus a half I. And the imaginary of our z is going to be -1/2. All right, example 3, write I to the power of 8 plus I to the power of 5 in the form a plus bi, where a and b are real numbers. So we want to convert this so that we have a real component and an imaginary component. The way we're going to do that is write it in terms of I squared. So this is I squared to the power of 4. So using our index laws, I squared to the power of 4, we multiply the powers, so that's going to be I to the power of 8. And then we also have I to the power of 4 times I. And now these we can define. So this we're going to get -1 to the power of 4. It's a an even power, so that's going to be +1. And then for this we're going to get I to the 4. So I to the 4 is going to be -1 squared, which is going to be +1, so that's plus I. So this will be 1 plus I. Okay, example 4. Simplify. Z equals I to the 4 minus 2I squared plus 1, and W equals I to the 6 minus 3I to the 4 plus 3I squared minus 1, and show that the sum of these two values is -4. So let's first simplify Z. So I to the 4, that's the same as I squared, so -1 squared, minus 2 times I squared plus 1. So now we can replace our I squareds with -1. So this becomes -1 squared is +1. 2 times -1 times -1 is going to be +2 plus 1. So that equals 4. Then for W, we're expecting it's going to be -8, but let's see if we can show that. So for this first one, we get I squared cubed minus 3I squared squared minus 3I squared minus 1. So this is -1 cubed, so that stays -1. This is going to be -3 times -1 squared, so that's +1, so this is -3. This is going to be -3 times -1, so that's +4 minus 1. So this is going to give us -1. Let me check something. I see the error. This is plus 3I squared. So that was me transposing the question incorrectly. So if that's plus 3I squared, I don't know why I said 4 in the first place, but that'd be -3, so we get -4. -4 is -8. So now we can see Z plus W is equal to -4, because it is 4 minus 8, which is equal to -4. There we go. All right, example 5. Just going through a bunch of different examples of finding the real of numbers. So the real of 7 plus 6i is, of course, going to be 7. The imaginary of 10, well, it's 10 plus 0i, so that's going to be 0. For the real of 2 plus I minus 3i cubed, we have to do some work first. So the real of 2 plus I, so we can rewrite that as minus 3i squared I. And even though this doesn't end up changing anything, because it's only going to change the imaginary component, we still want to check it. So that's going to be plus 3i. So that's 2 plus 4i. So the real of 2 plus 4i is 2. And then lastly, we've got 1 take 3i take I squared take I cubed. This one, it is important. It will change our solution. So 1 take 3i, take I squared, take I squared times I. This is going to give us 1 minus 3i plus 1, because it's negative 1 times negative 1, minus negative 1, so that's plus I. So this is going to give us 2 minus 2i, so the imaginary of 2 minus 2i is going to be negative 2. And that is all for this video. Thank you for watching.